3I Atlas is moving closer to Earth. On December 19th, it will reach its closest point to us. And the most recent images show something that should not happen at all. Look at its tail. It is pointing toward the sun, not away from it. Every comet we have ever studied does the opposite. Solar wind and radiation pressure always push a comet's tail away from the sun. That is basic, well-established physics. We have understood this for decades. Yet 3I Atlas has been doing the exact opposite for 5 straight months. It was doing it back in July while moving toward the sun, and is still doing it now as it moves away. So what is actually happening here? To understand why this is so strange, we need to look at how comet tails are supposed to work. When a comet approaches the sun, it heats up. Frozen gases on its surface begin to turn directly into gas, a process known as sublimation. As these gases escape, they drag dust particles along with them. This creates a coma, the fuzzy cloud that surrounds a comet's nucleus. Then the solar wind takes over. Solar wind is a constant stream of charged particles flowing outward from the sun at roughly 400 kilometers per second. When this stream collides with the gas and dust around a comet, it sweeps that material away from the sun, forming a tail. Solar radiation pressure reinforces this effect. Sunlight carries momentum. When photons strike tiny dust grains, they exert a small push. On its own, that push is weak, but over time it adds up. Together, solar wind and radiation pressure stretch comet tails into long structures that always point away from the sun. This is why the orientation of a comet's tail does not depend on the direction the comet is traveling. When a comet is approaching the sun, the tail appears to trail behind it. When the comet is moving away, the tail can appear ahead of it. But in every case, the tail still points in the anti-solar direction. You can see this behavior in every famous comet image ever taken. Halley's Comet, Hale-Bopp, Comet Neowise. In all of them, the tail is always on the side opposite the sun. A useful analogy is smoke from a campfire. The wind blows the smoke in one direction, regardless of where you stand or how you move around the fire. You could carry a torch around the campsite, but the smoke from that torch would still drift in the same direction as the campfire smoke, because the wind controls it. Solar wind works the same way. It flows outward from the sun in all directions. So any comet anywhere in the solar system should have its tail pushed away from the sun. We have observed hundreds of comets, and every one of them follows this rule. This is not a theoretical idea. It is an observational fact confirmed countless times. 3I Atlas does not follow this rule. On July 21st, 2025, the Hubble Space Telescope captured an image of 3I Atlas while it was still approaching the sun. At that time, it was about 2.98 times the Earth-Sun distance away. The image showed a bright, teardrop-shaped glow extending toward the sun, not away from it. This feature was obvious. It was not a faint detail that only appeared after heavy image processing. It was clearly visible in the raw data. A bright, elongated structure pointing in the wrong direction. Astronomers referred to this feature as an anti-tail, because it points opposite to where comet tails are supposed to point. At first, some researchers suggested it might be a perspective effect, essentially an optical illusion. In certain viewing geometries, parts of a dust tail can appear to point sunward even though they are actually pointing away in three-dimensional space from a particular angle. The curvature of the tail can make it look wrong. Based on that idea, many assumed the anti-tail would vanish after the comet passed perihelion, the point of closest approach to the sun. Once the comet began moving away, Earth's viewing angle would change, and the tail should appear in its normal orientation again. But that is not what happened. On November 30th, 2025, Hubble observed 3I Atlas a second time. By then, the comet had already passed perihelion on October 29th and was receding from the sun. It was about 1.91 times the Earth-Sun distance away. The anti-tail was still there. It was still pointing toward the sun. This sunward-pointing structure extended roughly 60,000 kilometers in the direction of the sun, about 10 times the radius of Earth. It was bright and clearly defined in the images. If anything, the anti-tail appeared sharper and more structured in November than it did in July. The edges were clearer, and the shape was more distinct. Whatever was producing this feature was not fading. It was persisting. This persistence rules out a simple perspective explanation. If geometry alone were responsible, the anti-tail should have disappeared or flipped direction once the comet passed perihelion. Instead, it remained fixed in orientation, continuing to point sunward. Amateur astronomers have also been monitoring 3I Atlas. Thousands of images have been captured by backyard telescopes around the world, using different equipment, at different times, and from different viewing angles. All of them show the same thing. The anti-tail is real. It has been present since at least July, and is still visible now. On December 13th, 2025, just days before closest approach to Earth, astronomer Tirasak Thaluang in Thailand captured an image showing the same sunward-pointing structure, with the same orientation and shape. This feature is stable and persistent, so if solar wind and radiation pressure push material away from the sun, what is forcing this material toward it? This is where the physics problem becomes serious. The anti-tail stretches 60,000 kilometers toward the sun. That is an enormous structure made of gas and dust, the same material that should be blown outward by solar forces. To maintain a tail pointing sunward, particles would have to be moving against the solar wind. That requires a force pushing them in the opposite direction, stronger than both solar radiation pressure and solar wind combined. What force could do that? Gravity pulls objects toward the sun, but gravity acts on the entire comet uniformly. It does not produce narrow jets or elongated tails. In addition, 3I Atlas is traveling on a hyperbolic trajectory, is moving fast enough that the sun's gravity only slightly bends its path. The comet's current speed relative to the sun is around 58 kilometers per second, well above escape velocity. Gravity is not capable of creating a focused 60,000 kilometer long structure of material pointing sunward. If gravity could do this, we would see anti-tails on every comet. We do not. Could the comet's rotation be responsible? Flinging material toward the sun? That does not work either. Rotation-driven outgassing produces jets that sweep around as the nucleus spins. It does not create a stable structure locked in one direction for 5 months straight. Rotation cannot explain a persistent, sunward-pointing anti-tail that refuses to change orientation. One possibility is that gas is venting from a region on the side of the comet facing the sun. In principle, that could produce a jet aimed sunward, but outgassing jets do not extend tens of thousands of kilometers. They usually reach only a few hundred, or at most a few thousand, kilometers before dispersing. They also change over time as the comet rotates and as sunlight heats different surface areas. This anti-tail behaves very differently. Its direction has remained essentially unchanged. Its length has stayed roughly the same. Its brightness profile has been consistent, and it has done all of this for 5 straight months. That kind of stability is not what we see from normal outgassing activity. There is another puzzling detail. On November 19th, 2025, NASA held a press conference about 3I Atlas. They discussed data from Hubble, from the James Webb Space Telescope, and from spacecraft orbiting Mars. They talked about the comet's composition, its size, and its trajectory through the solar system. But they never mentioned the anti-tail. Not a single time. That omission is strange, because the anti-tail is one of the most visually striking features of the comet. You do not need advanced training to notice it. Anyone who looks at the images can see it immediately. NASA certainly has those images. Hubble is their telescope. They process the data, release the pictures to the public, and then held a press briefing without addressing this feature at all. There could be several explanations. Maybe they consider it unimportant. Maybe they already have a working explanation and did not feel it needed public discussion. Or maybe they do not yet understand it and are waiting for more observations before saying anything. We do not know, but the lack of comment is unusual. Regardless of the silence, the anti-tail exists. It appears in thousands of independent observations, and it directly challenges the standard physics used to explain comet behavior. Astronomers have put forward 3 different explanations so far, and all of them are, to be honest, quite unconventional. One idea involves evaporating ice particles. This explanation was proposed independently by Eric Kito and Avi Loeb. The concept is that extremely small ice grains are released from the sun-facing side of the comet. These grains might be only about a micrometer in size and could be composed of water ice or carbon dioxide ice. As soon as they leave the surface, sunlight heats them and they begin to sublimate. The solid ice turns into gas, causing the particles to shrink rapidly. The crucial point is that as these particles sublimate, they lose mass and become lighter. Before solar radiation pressure has time to push them away from the sun, they completely evaporate. The result is a dense cloud of ice grains that exists only very close to the nucleus. These particles never survive long enough to be swept into a normal tail. Instead, they form a bright, sunward-facing glow concentrated on the side of the comet that faces the sun. From a mathematical standpoint, this scenario can be made to work. If the particles are small enough and if they sublimate quickly enough, they can produce a structure that resembles an anti-tail. In this picture, the grains are ejected from the surface, exist for only seconds or minutes, scatter sunlight during that brief lifetime, and then vanish because they are confined near the nucleus and predominantly on the sun-facing side. The scattered light appears as a glow extending toward the sun. An analogy is steam escaping from a kettle. The steam rises, but it does not travel very far before cooling and becoming invisible. You only see it close to the spout. In the same way, these ice particles would only exist near the comet's nucleus before disappearing. The problem is that this effect has never been observed on anything like this scale. Some small comets show a faint sunward glow when they are extremely close to the sun, but 3I Atlas displays a 60,000 kilometer long anti-tail, while it is 2 to 3 astronomical units from the sun. That is far beyond the distance where this behavior is expected. On top of that, 3I Atlas is not a tiny object. Estimates place its nucleus somewhere between a few hundred meters and several kilometers in diameter, is shedding a large amount of material for the evaporating ice particle model to hold. The comet would need to be producing a massive quantity of ultrafine ice grains, far more than has been observed from any other comet. It is not impossible, but it pushes the limits of what current comet physics can comfortably explain. Another proposed explanation is that the anti-tail is produced by a swarm of objects. This idea was put forward by Avi Loeb in a paper released on December 8, 2025, and is based on a measurement that has been confusing astronomers for months. Observations show that 3I Atlas is experiencing non-gravitational acceleration. In other words, is not moving along a path determined solely by gravity. Something is giving it a small but measurable push. The comet is accelerating away from the sun by an amount that cannot be explained by solar gravity alone. This kind of behavior is not unheard of in comets. Outgassing can act like a weak propulsion system. When gas escapes more strongly from one side of a comet, it produces thrust in the opposite direction. Similar to a tiny rocket engine, the force is small, but over time it accumulates and slightly alters the object's orbit. In the case of 3I Atlas, this non-gravitational acceleration has been clearly detected. The effect is real, and it shows the comet is being pushed outward from the sun lobes. Proposal builds on this. Suppose 3I Atlas released a large number of objects at some point, possibly during perihelion when it was closest to the sun, or perhaps even earlier. These objects could be fragments, boulders, or clumps of dust, if the main nucleus is being pushed away from the sun by outgassing. But these detached objects are not experiencing the same thrust. Then they would fall behind. They would remain closer to the sun while the nucleus slowly pulls ahead. The distance of this lag would depend on how strong the non-gravitational force is and how long it has been acting. Loeb calculated that at the comet's current distance from the sun, material that does not share the nucleus's acceleration would end up about 54,000 to 60,000 kilometers closer to the sun. That range almost perfectly matches the observed length of the anti-tail. The most intriguing part of this idea is how brightness works. A cloud of many small objects has a much larger combined surface area than a single solid nucleus, even if the total mass of that cloud is only a tiny fraction of the comet's mass. For instance, if just 1% of the comet's mass were broken into trillions of tiny fragments, Their combined surface area could be hundreds of times greater than that of the nucleus itself. A simple analogy helps here. Take a basketball and smash it into 1,000,000 pieces. The total mass stays the same, but the exposed surface area increases dramatically. The same principle applies in space. More surface area means more sunlight reflected. That makes the swarm bright enough to appear as a distinct structure in telescope images. And because this swarm would consistently lag behind the nucleus by roughly the same distance, it would naturally form a stable anti-tail pointing toward the sun. This explanation aligns neatly with the observations. The predicted separation matches the measured length of the anti-tail. The brightness is accounted for by the large surface area of many small fragments. And the long-term stability makes sense because the swarm would maintain a nearly constant offset from the nucleus. The unanswered question is where this swarm came from. Did 3I Atlas partially break? Apart during perihelion? Did it shed a shell of material long before that? Is this kind of fragmentation normal for interstellar comets? Or is this something entirely new? At this point, no one knows. There is also the possibility that neither explanation is complete. It may be that we are missing an entirely different mechanism. The evaporating ice particle model can be made to work mathematically, but it requires conditions that have never been clearly observed. The swarm model fits the data well, but it depends on a fragmentation event that no telescope actually witnessed. It is also possible that the real answer involves a combination of effects, or that interstellar comets behave in ways we do not yet fully understand. The only way to resolve this is with better observations. December 19th, 2025 marks 3I Atlas's closest approach to Earth. Even then, it will still be about 269 million kilometers away, but this will be the nearest it ever comes. That date also coincides with a new moon, meaning the sky will be especially dark, with no moonlight interfering with faint details. From an observational standpoint, the timing could not be better. Multiple instruments are already scheduled to observe the comet, including Hubble, the James Webb Space Telescope, and ground-based observatories across the globe. Scientists will be collecting every possible measurement. One of the most important things to determine is the speed of the material forming the anti-tail. If it consists of evaporating ice particles, those particles should be moving at thermal velocities, typically a few hundred meters per second, perhaps reaching up to a kilometer per second if they are strongly heated. If the anti-tail is instead made of solid fragments or something else entirely, the measured speeds could be very different. Higher speeds would point to a different mechanism, while unusually low speeds would suggest something strange about the dynamics. Spectroscopic data will reveal what the anti-tail is made of. If the signature shows water ice or carbon dioxide ice, that would support the evaporating particle explanation. If it turns out to be dominated by dust, rock, or unexpected compounds, the interpretation would change significantly. The same measurements will also tell us more about the comet itself, including which volatile substances it is releasing, in what quantities, and at what rates. Astronomers are particularly interested in the ratios of different molecules, the balance between water vapor, carbon dioxide, carbon monoxide, methanol, and other compounds carries information about the temperature and pressure conditions under which the comet formed. These ratios act like a chemical fingerprint, revealing clues about the comet's origin and history. High-resolution imaging will also be crucial. Researchers want to see whether the anti-tail changes as the comet approaches Earth. Does it brighten? Does its shape evolve? Does it fragment or vary in length? Each of these details provides insight into the physical process behind it. When dealing with a mystery like this, no observation is trivial. This is a one-time chance. 3I Atlas is on its way out of the solar system. After passing Earth, it will continue outward, reaching the region near Jupiter by around March 2026 before disappearing into interstellar space. Its orbit is strongly hyperbolic, with an eccentricity greater than 6, meaning it will never return. This is not like periodic comets such as Halley's Comet, which revisit the inner solar system on a predictable schedule. Once 3I Atlas is gone, it is gone forever. That means the observations gathered over the next few weeks are all we will ever have. Those data will decide which explanation holds up, or whether an entirely new theory is required. For 5 months, the anti-tail has stubbornly pointed toward the sun. It has not faded, flipped, or vanished. Soon, we will finally learn why. What do you think explains it best? Evaporating ice particles, a swarm of fragments, or something we have not yet imagined? Let me know your thoughts. And stay tuned for the December 19th observations, because real answers are finally within reach.